Alright, what we're going to do in this video is look at one of the Falstad applications. This is the 2D electrostatic field applet, and this should look very similar to what we saw on the FET site, where we had a point charge in the middle, and there were all these little contour lines, and they're so close together we can't actually even resolve them as separate lines here. And then they get further and further apart as we go out. And now each of these differences here actually is going to represent, from here to here for instance, and from here to there, represent the same change in voltage, or the same electric potential change. This very much so represents the landscape of basically the world from the point of view of a charge. And what I'm going to do now is I'm going to get rid of the flat view, and I'm going to show you what this looks like then. So this would be actually a negative charge. Is going to give you this type of a feature. And you can see it's very, very steep down in the middle there. But this is what the world will look like to a positive test charge. So a positive test charge comes along, and I can actually show you this. Let's look at what happens to these positive test charges. So out towards the edge, they're just kind of slowly falling in, but as they get further and further along, obviously they're going to speed up because there's forces acting on them for a while. And also those forces get greater and greater and greater. The landscape gets steeper and steeper and steeper, so they fall in faster. This is great for showing us what happens from the point of view of a positive test charge. But if we have a negative charge, let's say we have an electron and we want to know what happens to that. Well, the great thing about electric potential is that it's a landscape. It doesn't care what type of charge we put nearby. Whether these are positive test charges or negative test charges, the landscape still looks like this. The difference is that while positive test charges do what they're supposed to do, they fall in towards this big pit here. Negative charges do the opposite of what they're supposed to do, or what we would think that they're supposed to do. So a proton would fall into a hole. An electron would fall up a mountain. That's the natural thing that it wants to do. Positive charges want to get as low as possible because that's where the negative charges are. So this is a negative charge. They want to fall into that. A negative charge, if I put a negative test charge out here, it wants to get away from this pit as much as possible and rise up as high as it can. That's its version of falling. And I'm going to hopefully be able to show you a little bit. Oops. Don't want that right now. Actually want a dipole. Here we go. So now we have a positive charge and a negative charge. This is the positive charge, this is the negative charge, and this is actually too steep in here for us to really even see what's going on. I just reduced the field strength by quite a bit. So these are now not very, the field strength isn't very, very strong anymore. And you can see there's not a whole lot of movement out here. But you do see this sort of general swirling around. They're coming out this way, they're swirling around over this way, and vice versa. But the most of the action is in between these two things. And I can slow that down by separating them out a little bit. And you can see there's definitely still a slight slant, and that's where they're falling. But in general, the steepest parts are in here. And I'm going to go ahead and change this to the flat view. And you can see this is the positive, this is the negative over here. They kind of reverse positions on us. These contour lines are very, very close together here. That means it's very, very steep. The electric field is really strong in these regions, and it becomes weaker as we get in here. And what I'm going to do now is I'm actually going to show you the field lines. So these are what the field lines look like, and they do show us, and I can't quite show everything at once. Let's see. So these are now representing the potentials. And you can see that they fade. They're strongest in the middle, and they start to fade off towards the sides. But these field lines are radiating in such a way that they're always perpendicular to the equipotential lines. I'm going to go back and put on the field magnitudes and get our equipotential lines back. We're not going to play with these just yet. Now, back to this. I can change the charge separation. I can make it really, really close to each other, And so now we have really fast moving particles, even though the field strength isn't that great, because it's just so steep everywhere that we get the positive test charges falling off of the mountain and falling into the pit. I really strongly encourage you to try as much as possible when you see things like this. I'm going to go to a quadruple. When you see problems involving voltage, or really any problems involving charge, that you imagine a landscape based on the voltages. And the landscape is correct for positive test charges. And what I mean by correct is that a positive test charge will do exactly what you would expect to happen if this was like a gravitational type of situation. So I put a ball up here somewhere, and it's going to fall down and fall into this pit then. A negative charge will do the opposite of what we expect. It falls up rather than falling down. But otherwise, it's a pretty perfect analogy for what's really going to be happening. It's a very convenient mechanism to use, to think of the landscape, and then to apply that landscape to particular charges to figure out what's happening in a particular circumstance with the charge. But the landscape idea is very, very, I think, useful. One of the things that I'll talk about is using a model in your mind of like bed sheets. So you get a bed sheet, you kind of stretch it out a little bit, and you put a mass in it. And what's it going to do? It's going to depress that bed sheet. And so by depressing the bed sheet, you basically just put in a negative charge in there. And everything that you put on the bed sheet then, every normal thing, and by normal things I'm going to mean positive charges, they're all going to be sort of attracted in to that center point. On the other hand, if we lift up bits of the bed sheet, if we just pinch a little bit of the bed sheet and we lift it up, we form like a peak, very similar to the ones that we have here. And by forming those peaks, now anything that we put on that sort of pinched and raised up area, we're going to fall down. So I oftentimes imagine, I either draw out specifically what I think is going to happen, or I imagine like a bed sheet being pulled up or pulled down and things rolling along the surfaces. Because it does give you a visual understanding of what's happening beyond what you get if you just try to mathematically solve the situations. And sometimes solving mathematically without visualizing is a very, very bad idea. I highly encourage you to play around with these different simulations to get used to this way of thinking. There will be some questions that do incorporate these. I'll be asking you questions on, for instance, where might the potential be zero, and hopefully you can tell the zero is, where it's pretty flat. What's going on with electric fields at different areas, that type of thing, where it's the steepest, where it's the least steep. So all these types of questions are fair game, and it's going to be most helpful for you if you have some sort of an understanding of how this works.